In this example, we are asked to determine the radius and the interval of convergence of this power series. So let me name this power series, P of x. It's the sum as n goes from 1 to infinity of this ratio, n over 2n, 2 to the power n, times, parentheses, n squared plus 1, all times x to the power n. So before we get too deep into this is our first example of checking a power series for the radius and interval of convergence. Remember, the radius of convergence is just a number. So the radius of convergence is a number. The interval of convergence, I'm just going to call it I or IC. This is an interval that could be half open, totally open, totally closed. In other words, we need to do a lot of work to find this interval. But the interval is always of the form x minus x naught less than r before we check the endpoints, right? Where in this scenario, the r is the number that we found from the radius of convergence when we get to that point. And the x naught, this is the center. This is the center of our power series. And remember, the general form of a power series is that it should look like P of x equals the sum as n goes from something to infinity. In this case, it's 1, so I'll write it the same way. 1 to infinity, c sub n times x minus x naught to the power n. And the c sub n's are the coefficients, right? So they correspond to this ratio where there's just n's and no other x's in our function. And the x naught, this minus x naught, this is the center. And that doesn't show up here, right? So for us, x naught must be 0 for this power series. Okay? So what we need to do is apply the ratio test to determine r. Now remember how we set this up in the instructional or the introduction video. We said that what we should do is we should perform the ratio test on the coefficient series. So we're going to take c sub n plus 1 over c sub n, and we're going to find the limit of this ratio, right? So c sub n plus 1, that is the terms of that series, c sub n plus 1, are the terms of this series with all the n's increased by 1. So I'm going to write this in a different color. Let's do it in red. So we always have this absolute value here. C sub n plus 1 is then n plus 1 divided by 2 to the power n plus 1 times, parentheses, n plus 1 quantity squared plus 1. Okay, and then what we have to do is divide by the series c sub n, but that's just the same as multiplying by the reciprocal of this series. So I'm going to write this as multiplying by the reciprocal, 2 to the n squared plus 1 over n. Okay, and then we can kind of regroup stuff here. Notice that nothing here is negative, so we can actually forget about the absolute value. That doesn't always happen, so be careful. But what we can do then is group this as n plus 1 divided by n. So there's something. Then we can write the next term as, so then we have times, let's look at the 2's, right? So the next term here is 2 to the n over 2 to the n plus 1. And the next term is going to be this n squared plus 1 over this term, right? So then we have n squared plus 1 divided by this term in the denominator. We can multiply out if we want to. This will be n squared plus 2n plus 1 plus 1. So n squared plus 2n plus 2. Okay, and now we want to take the limit of this whole thing. So we're going to take the limit of this whole thing as n approaches infinity. But as we do so, we can, remember, if these are all convergent, then they're going to converge, or even if one diverges. But we can break this up and multiply the limits, right? So we can consider each one of these limits individually and multiply up the answers as long as the answer makes sense, right? And we just look at these. So as n approaches infinity of this first term, for this first term, n over n, this is just a leading coefficient test. This term just approaches 1, right? So there's 1. The second term, I'll switch colors here. So the second term, we have 2 to the n over 2 to the n plus 1. Well, 2 to the n plus 1 is just 2 to the n times 2. And when we take this limit, we can cancel. And that limit, you always cancel powers of n, right? In the limit, as long as the limit's with respect to n, that limit's going to be a half. And then finally, this last one, again, change the color here. This last one is again a leading coefficient test. As n gets very large, the highest power rules, and this is another 1. And so what we learn then is that the limit of the coefficients, the ratio of the coefficients, this is our L. Our L is equal to a half. All right? Now, that is not the ratio, or the radius of convergence, I should say. That is the limit of the ratio of the coefficients, but it doesn't factor in the x's, right? And so what we decided in our last introduction video was that the radius of convergence is always the reciprocal of L. So in this case, the reciprocal of L is not 1/2, but it's 2. So the radius of convergence of this series, this power series, is 2. All right, that leads us then to the next question, which is, what is the interval of convergence? Well, the interval of convergence is always centered around, it's centered around the center point, which we said for us is 0, right? And so the interval of convergence is going to always be, if this is 0, it's at least x less than r, right? So for us, that means our absolute value of x is going to be less than 2, or our interval is at least the interval from -2 to 2. I keep saying at least. Why am I saying that, right? Well, that's because we need to check. We need to find out what happens at these boundaries, right? When x is either equal to 2 or equal to -2. Can we tell what happens at these boundaries? So, to do that, we actually have to plug in the values for x and check that. Okay? We have to actually check it because the ratio test is inconclusive at these boundary points. It doesn't mean that it's not inconclusive, does not mean that it's not convergent, right? It could be convergent. It just doesn't tell us anything. We have to check. So now we have to do more work. We plug in the two endpoints. Let's start with x equal to 2 for the first endpoint. Our power series becomes the sum, n goes from 1 to infinity, n over 2 to the n times n squared plus 1 times x to the n. X to the n is now, I'm plugging in, I started with the right endpoint. I started with 2. So if I'm starting with 2, this becomes now times 2 to the power n, right? Notice that here's a 2 to the n on the bottom. Here's 1 on the top. Those cancel, right? Those are going to cancel. And what's left? So the series at this point, when x is equal to 2, our power series becomes an honest, legitimate series with no x's left in it, right? And we need to test, does this series converge or diverge? So the series n, so the series as n goes from 1 to infinity of n over n squared plus 1. All right? This one can be done a couple of different ways. This one is actually okay for an integral test. This one is actually probably fine for a comparison test, but I'm going to do this one by a limit comparison test. So limit comparison test. And the series that I'm going to compare this with is just 1 over n. So 1 over n. So remember how the limit comparison test works. It's almost like the ratio test. You take the ratio of these two, and you take the ratio of these two, and you take their limit, right? So the limit comparison test will then say that I should take n over n squared plus 1 divided by 1 over n, or times n over 1. This is n squared over n squared plus 1. All right? And so as n approaches infinity, this limit approaches 1. And well, what does that tell us? 1 is not good news if you're doing the ratio test, right? 1 in the ratio test is inconclusive. But in the limit comparison test, as long as you get as long as you get a constant that's neither 0 nor infinity, infinity is not a constant anyway, but if you get a non-zero constant here, then what you learn is that the series in question, this one, has the same behavior as the series that you compared it to. So the series n goes from 1 to infinity of 1 over n. These two series have the same behavior. Well, what do we know about this series? This is the harmonic series, right? And it is divergent. So we just compared to a divergent series and we got an affirmative answer. So what does that tell us? Well, it tells us that this series is also divergent. All right? So this series in question also diverges. And so our answer up here is that we should not include x equals 2 in our domain. All right, we have to check the other endpoint now. When we check x equals -2, what happens? It's very similar. Now our series is going to be, just put a little squiggle here. Our series is going to be n goes from 1 to infinity. N times, this time it's going to be -2 to the power n over 2 to the power n squared plus 1. Okay. When we try to do our cancellation here the same way we just did it with the right endpoint, we can cancel the 2's, but it leaves behind a -1 upstairs. -1 to the power n upstairs. Okay, the 2 to the n's cancel. -1 to the n stays. And so what we end up with here is that this sum, n from 1 to infinity, -1 to the n over n squared plus 1. This appears to be an alternating series. Okay, it's very similar to the one we just looked at, except it's got this alternating term. And I'll let you work out all the details of the alternating series test, but remember what you have to check is that number 1, n over n squared plus 1 should be strictly positive. Okay, I'm going to say check mark, but you should check that. You can always pause and ponder, stealing a term from 3 Blue 1 Brown, but you can always pause this video, think about that for a minute, and check that that's truly positive. The other thing you need to check is that this is decreasing, so that n plus 1 over n plus 1 quantity squared plus 1, this should be less than n over n squared plus 1. All right, and there's different ways to check that. I'm going to also put a check mark there, that that is decreasing. Again, you could do this by replacing this side with a function, taking its derivative, showing that the derivative is eventually negative, or you can do some argument comparing these, some cross multiplication and some comparing of the two different sides. But once you've checked this criteria, then you just take the limit as n approaches infinity, of course, of n over n squared plus 1. And as long as that's 0, which again it is, then this series is actually convergent, right? Convergent. But this is convergent by the alternating series test. This is an alternating series. So that means that we do include the endpoint x equals -2. So after all this work, we found the radius of convergence is 2. We wrote down this kind of preliminary interval of convergence. Then we checked the two endpoints. The right endpoint is not included. That was a no. The left endpoint is included. That's a yes. And so our final answer for the interval of convergence, we already got our radius of convergence, but after a lot more work, the interval of convergence we found is that for this series, the interval of convergence is the interval -2 less than or equal to x less than 2. The left endpoint is included, the right endpoint is not included.